Welcome to Eridanus Light, where we trace the ideas that built the cosmos. Today, we begin a journey not through space, but through thought, the mind of a man who shaped how we understand the universe itself. A man whose shadow falls across every telescope, every equation, every spacecraft. This is the story of Aristotle, a man who reached for the stars with nothing but his senses and gave birth to the foundations of science. Imagine it's 2,400 years ago. You're in a courtyard, the cicadas buzz, olive trees rustle in the Athenian breeze. A man holds a feather in one hand, a stone in the other. He drops them. The stone hits first. He nods, scribbles on parchment. That man is Aristotle. He's not testing gravity. Not yet. He's testing why. Not what falls faster, but what does it mean when it does? This question, simple, physical, grounded, starts a fire that burns through human history. Before rockets, before physics, before formal science itself. And yet, here is the beginning. Born in 384 BCE in the town of Stagira in northern Greece, Aristotle grew up in a world where medicine and observation weren't separate from the sacred. They were intertwined. His father, a royal physician, introduced him to a discipline that demanded attention to cause and effect. While others memorized myths, Aristotle learned anatomy. The boy didn't worship the stars, he questioned them. This restless curiosity would carry him to Athens at 17, into the arms of the greatest philosophical mind of the time, Plato. Plato believed in unseen ideals, that everything physical was just an echo of something perfect. But to Aristotle, that was like ignoring the smell of rain, the scratch of stone, the heartbeat of the world. The tension was inevitable. Where Plato soared, Aristotle stood grounded. 20 years of mentorship turned to friction. After Plato's death, Aristotle didn't inherit the academy. He walked away. He wandered Asia Minor. He studied. He returned with experience, not just theories. And when he came back to Athens, he brought something radical. Not a temple to abstraction, not a lecture hall of gods and metaphors, a workshop for reality. At the Lyceum, the world itself was the textbook. Students strolled under trees, asking questions about everything. Light, heat, dreams, bees. They dissected, measured, compared. This wasn't just education, it was the invention of method. In a world where knowledge was inherited, Aristotle proposed it could be built. And so, the Lyceum became the first engine of empirical science. What do you get when you mix philosophy with biology, ethics with astronomy, logic with politics? You get a map of existence, one drawn by a single hand. He didn't separate disciplines. He saw them as organs of the same body. Imagine that same courtyard at night. No light pollution, just infinite dark pierced by flame-like stars. To others, those stars were gods, stories, prophecies. To Aristotle, they were clues. Why do stars move in arcs, never erratically? Why does the sun rise and set like clockwork? Why does the moon grow and shrink in perfect rhythm? But the planets, the planets, they betrayed the pattern. They wandered, retrograde. To make sense of it, Aristotle built a model, Earth at the center, surrounded by transparent crystalline spheres, one for each celestial object, spinning in harmony. Was it accurate? No. Was it a breakthrough? Absolutely. For the first time, someone tried to explain the cosmos without invoking divine whim. He used geometry. Reason. That model would hold for nearly 2 millennia, not because it was flawless, but because it was a framework, a place to start. Long before telescopes, Aristotle looked to the moon during an eclipse. He saw the Earth's shadow curve across the lunar face, not jagged, not square. When sailors ventured south, new stars rose on the horizon. Conclusion? Earth was a sphere, not a theory, a deduction. And from that deduction, we arrive at our satellites, GPS systems, orbital mechanics. The leap from curved shadows to spaceflight is steep, but it's the same ladder. Aristotle didn't just describe the world. He wanted to understand how to understand it. Interlogic. His syllogisms weren't just parlor tricks. They were blueprints for reasoning. You take two truths, combine them, and out comes a third. This is the basis of programming, of AI, of legal arguments, of scientific deduction, if-then statements. That's Aristotle. Decision trees in Mars rovers? Aristotle. Cognitive behavioral therapy? Still Aristotle. He made thought itself mechanical, without making it robotic. He gave humans a way to test their beliefs, to structure doubt. And in doing so, he made progress possible. With knife in hand and curiosity in heart, Aristotle cataloged life. Fish with lungs, insects with strange metamorphoses, cephalopods with intelligence. He noted how embryos formed. He puzzled over how traits passed on. He saw purpose not just in anatomy, but in behavior. His classification system wasn't perfect, but it was a system. He saw life as layered, ordered, understandable, and from that he planted the seed of taxonomy, of comparative anatomy, of evolution. Today's biologists on the International Space Station, studying how cells behave in zero gravity, they're still building on Aristotle's vision. The tools have changed. The mission remains. There's a beauty in how Aristotle imagined the cosmos. He didn't see chaos. He saw order, music. He believed the spheres produced sound, a cosmic harmony too perfect for human ears. We now know there are no spheres, but the harmony, it's real. Black holes merge, and the fabric of space-time ripples. We convert those ripples into audio. We listen to collisions older than humanity. Aristotle imagined music. We recorded it. Wrong in the mechanism. Right in the metaphor. What did Aristotle really leave us? Not just facts, not just flawed models. He left us courage, the courage to ask questions with no promise of answers. He left us rigor, the demand that ideas match the world, not just each other. He left us wonder, not passive, but active. The kind that builds laboratories, launches rockets, and rewrites textbooks. You live in a world he helped invent. Every time you map a theory, test a claim, peer into a microscope, you stand in his shadow, not to worship it, but to outgrow it. Because that's what he wanted, not agreement. When we left Aristotle, he had laid down the first framework for understanding the universe. Observing, questioning, building a method out of what others called mystery. But the sky still held more riddles. The stars had patterns. The sun had rhythm, but there were motions that defied sense, dances of planets that broke the beat of cosmic harmony. And Aristotle saw this not as chaos, but as a deeper logic waiting to be uncovered. The Greeks had a word for planets, planetses. It means wanderers, because that's what they did. Venus, Jupiter, they slipped, they reversed, they drifted. Backward motion, retrograde, was no illusion. It was a puzzle. To Aristotle, these weren't gods misbehaving. These were phenomena crying out for reason, so he built a model. Earth at the center. Around it, the moon, the sun, the planets, all embedded in transparent, nested crystalline spheres. Each orb rotated at its own divine speed, interconnected like gears in a cosmic clock. This was no myth. This was Aristotle doing what had never been done, using geometry and consistency to explain why the heavens moved. Wrong? The heavens were no longer above questioning. They were now part of physics. Why circles? Because to Aristotle, the circle was the most perfect shape, eternal, without beginning or end. He believed the heavens, unlike Earth, were unchanging and divine, made of a fifth element, ether. And what kind of motion fits the divine? Constant circular motion. So, when the planets acted strange, like moving backward, he didn't throw away his model, he refined it. Others after him, like Ptolemy, added epicycles, little circles riding on bigger circles, to make the math work. It wasn't pretty, but it worked. For centuries, these models could predict eclipses, planetary positions, even comets. The math was right, the model was wrong. But until better data came, it was the best science had. You might ask, why does this ancient geocentric model matter in a world of space telescopes and black holes? It was about creating a system that demanded coherence. Before Aristotle, celestial events were interpreted, omens, divine messages. After Aristotle, they were explained. The sun doesn't rise because Apollo rides a chariot. It rises because of rotation. But that idea that there's a reason behind the motion was born with Aristotle's spheres. He taught us to expect rules. And that expectation drives science today. When the James Webb Telescope maps exoplanets, it does so on the assumption that physics works out there the same way it does here. That assumption? Aristotelian. Aristotle believed Earth was made of four elements: earth, water, air, and fire. Each had its natural place. Earth and water fell. Air and fire rose. Why? Because nature seeks balance. Heavy things belong low. Light things rise. Drop a rock, it falls. Release smoke, it climbs. So when he looked at the stars and planets, he reasoned, these do not fall, so they must be made of something different, something unearthly. This divine substance didn't follow the rules of weight or gravity. It just moved, perfectly. Modern science has discarded ether. But here's the twist. We still separate realms. There's earth science, there's planetary science, there's astrophysics. We still recognize that different rules often appear to govern different scales. until we unify them. Here's where Aristotle's elegance became a trap. He believed heavier things fall faster, so a 1 kilogram stone should fall slower than a 10 kilogram one. It seems obvious, until Galileo rolled balls down ramps and proved otherwise. Aristotle's belief wasn't born of laziness. It was born of logic applied to bad data. He didn't have stopwatches, or high-speed cameras, or vacuum chambers. He had observation and intuition. And sometimes intuition lies. The tragedy is that because his authority was so vast, his errors became law. No serious challenge to his motion theory came for 1,800 years. And without the right motion theory, you can't launch rockets, can't predict orbits, can't escape gravity. So yes, Aristotle delayed the space age, but he also made it possible, because you can only disprove what someone has dared to claim. Aristotle didn't just map the sky, he gave it rhythm. The turning of the outermost sphere, the fixed stars became the measure of time. He didn't invent clocks, but he helped us believe that the universe itself was a clock, ticking, turning, and from that came calendars. Agriculture, navigation, our lives synchronized with the heavens, all because someone asked, what if the stars are part of the same world we are? In the 1600s, Galileo looked through his telescope and saw moons orbiting Jupiter. Not everything circled Earth. The crystalline spheres shattered, literally and metaphorically. But the idea of system, of structure, of cause survived. Aristotle gave us the courage to map the sky. Even when he was wrong with rigor. And in science, that's everything. Because you don't leap from mythology to Mars rovers in one go. You build models, and you break them, and in their ruins, you find the stars. Flash forward to 1969. Apollo 11 is preparing for lunar descent. The onboard computer is running calculations. Gravity, velocity, burn time. Those numbers obey Newton, not Aristotle. But the idea that numbers can describe motion, that the heavens follow rules, that's Aristotle. The trajectory is modern, the launch is digital, the foundation is ancient. Aristotle believed in purpose, that everything had a final cause, a reason for being. Today, we speak of function, not purpose. But the hunt is the same. Why do galaxies spin? Why does dark matter exist? Why does the universe expand? He gave us the instinct to ask why. He gave us the structure to pursue it. And he gave us the humility to know that every answer may open 10 more questions. Aristotle's cosmos was wrong, but it was coherent. It gave generations a scaffold to climb. And in climbing, we outgrew it. Today, we see galaxies 13 billion light years away. We model the Big Bang. We detect gravitational waves. But we still ask, what moves the stars? What keeps order in motion? What makes the universe make sense? And in asking, we follow him. Because the real center of the universe was never Earth. It was curiosity. And on that, Aristotle was exactly right. The sky was no longer divine. It was a clock. And the Earth, once thought to be the immovable heart of all things, was now a stage for laws and logic. But if the heavens had rules, then surely Earth did too. And if motion above could be studied, so could motion below. Now, imagine the world before physics. No Newton, no equations, no concept of inertia or force. What did it mean to move, to fall, to stop? Aristotle answered with what he knew: sight, sound, touch. The senses were his instruments, and from these he built the first theory of motion. Aristotle didn't just ask what happens, he asked why. Why does a leaf fall? Why does a horse gallop? He believed that every event, every motion, could be explained by 4 causes. 1. Material cause. What is it made of? 2. Formal cause. What gives it shape? 3. Efficient cause. Who or what made it? 4. Final cause. What is its purpose? Let's say you're looking at a space shuttle. Saw, the metal and composites. Its aerodynamic shape, formal cause. The engineers and tools, efficient cause. Efficient cause, to reach orbit, final cause. Modern science focuses on efficient causes, but final causes, that's where Aristotle saw meaning. To him, nothing was random. Everything moved toward an end. A seed becomes a tree. A child becomes an adult. A rock falls because its nature pulls it toward the earth. Today, we may scoff at purpose. But isn't that what we still seek? Why does the universe expand? Why do black holes radiate? Why are we here? The questions remain. Aristotle divided movement into 2 types: psi, natural motion. Things moving toward their natural place. Violent motion. Things being forced from it. So, a rock falling was natural. Smoke rising was natural. But pushing a cart? Throwing a spear? that was violent. He believed that objects only moved violently as long as a force acted upon them. The moment that force stopped, the object stopped too. That's why he thought arrows kept flying, because the air behind them kept pushing them forward. Was this wrong? Yes, but only in hindsight. He lacked frictionless surfaces, vacuums, and clocks. What he had was intuition, and intuition told him that motion needs constant effort. But Aristotle's idea planted the seed. It took Galileo and Newton to dig it up and replant it in better soil. Still, without Aristotle, they wouldn't have known where to dig. To Aristotle, everything on Earth was made of four elements. Earth, heavy, dry, solid, water. Heavy, wet, flowing, wet, air. Light, wet, moving, wet, fire. Light, dry, rising. Each element had a natural motion. Earth and water fell. Air and fire rose. He believed that the natural place of Earth was the center of the universe. That's why rocks fell. This model, though flawed, influenced everything from alchemy to medicine to astronomy. And what's fascinating, in space science, we still look at elemental behavior under new conditions. How does fire burn in zero gravity? How does water behave in orbit? How do gases expand on Mars? We've moved beyond Aristotle's four elements, but not beyond his curiosity. He asked, what is this made of? Where does it want to go? These are still questions we ask when sending probes to Titan or building habitats on the moon. If you drop a hammer and a feather, what happens? On Earth, the hammer hits first. To Aristotle, this confirmed that heavier things fall faster. He thought that weight determines speed. Simple, logical, but wrong. Galileo would later prove on a slanted ramp that all objects fall at the same rate, regardless of mass. And Apollo 15 would famously drop a hammer and feather on the moon. With no air resistance, they struck the ground at the same time. But Aristotle's mistake is more than a footnote. It teaches us that science is a story, not of answers, but of revisions, and every mistaken theory is a rung on the ladder. Aristotle believed that nature abhorred a vacuum, that empty space, void, could not exist. Why? Because motion in a void made no sense. If nothing's there, what resists? What carries? What pushes? To him, all motion required a medium air, water, something. For 2,000 years, this idea held. The cosmos, philosophers believed, was full. It wasn't until the 17th century that scientists like Torricelli and Pascal created vacuums and proved otherwise. And yet, the echo of Aristotle's fear still exists. Today, physicists ask, is space really empty, or filled with quantum fields, dark energy, vacuum fluctuations? Even now, the void isn't empty. Aristotle didn't create equations, he didn't graph trajectories, but he laid the philosophical groundwork. He taught us that motion is not magic, it's governed. When you launch a satellite today, you use Newtonian mechanics, yes, but the mental leap began with Aristotle, that what moves has reason, that falling, flying, floating, these are not mysteries, they are patterns, and patterns can be understood. He built the scaffolding that Galileo and Newton would one day rebuild with stronger steel. Aristotle believed that heavier objects move slower, not just because of mass, but because of resistance from the medium. And in a way, that's not entirely wrong. In air, feathers do fall slower. In water, movement is sluggish. Resistance matters. What he lacked was the idea of vacuum testing. Today, engineers simulate zero gravity to test satellite deployment. They remove air to test resistance, free motion. But the questions he asked, they're the same. To Aristotle, an object stops moving because its force has ended. Push a ball, it rolls. Then it halts. To him, the force was gone. Therefore, so was motion. In modern physics, we say it's friction, an external force acting against the motion. But think deeper. Isn't this how we perceive life too? We think momentum stops because the drive is gone. But maybe there's friction, resistance, not lack of purpose, but pressure from outside. Aristotle's physics and human psychology often rhyme. He gave motion a story, a struggle, a goal. Without understanding motion, you can't build rockets, you can't plan orbits, you can't land on Mars. Even Newton's laws stand on Aristotle's grave. Because to overturn a system, you must first have one. That was Aristotle's gift, not eternal truths, but eternal frameworks. He gave us a sandbox. Aristotle believed the universe had a purpose, that everything moved toward its best form, and in a strange way, that shaped his ethics too. He thought humans, like objects, had natural motion toward virtue, wisdom, fulfillment. To move well was to live well. Today we separate physics from philosophy. To him, understanding how a stone falls and how a man should live were part of the same story, a story of nature, motion, and purpose. So the next time you watch a rocket rise, a drone hover, or a satellite drift in orbit, remember the man in the olive grove. He had no tools, no engines, no labs, just eyes. Stones fall, leaves dance. And from these, he built the first physics. Wrong? Often. Irrelevant? Never. Because his was the first voice to whisper, motion is not chaos, it is law. And all science since has been the echo. So far, we've watched Aristotle shape the heavens with crystalline spheres and define motion with unseen causes. But now, the story turns to the earth itself, to the crawling, swimming, breathing, pulsing life that surrounds us. We enter a new realm, biology. And in it, Aristotle wasn't just a philosopher. He was a pioneer, long before microscopes, long before genes, long before Darwin. There was a man standing at the shore, dissecting sea creatures, cataloging birds, and daring to ask, what is life? What makes it grow? What makes it what it is? In the Aegean Sea, on the island of Lesbos, Aristotle built what could only be described as one of the world's first biological research centers. There, alongside his students, he observed marine animals firsthand, cutting them open, recording how they moved, bred, and fed. He didn't just speculate, he watched. The sea urchin, the cuttlefish, the dogfish, shark. Aristotle wrote about over 500 species in meticulous detail. He identified organs, structures, and systems. He noticed patterns, differences between blooded and bloodless creatures, between live birthing animals and those that laid eggs. He even spotted how dolphins nursed their young centuries before anyone else believed dolphins were mammals at all. This wasn't mere curiosity, it was classification. And from that came a structure that would echo through the centuries. To make sense of the complexity, Aristotle proposed what became known as the Scala Naturae, the great chain of being, a vertical hierarchy of life, from the simplest organisms to the most complex. At the bottom, plants, then simple animals, then more complex animals, then humans. This was not evolution. It wasn't about change over time, but it was about order. He ranked organisms by their ability to sense, to move, to think. And though the latter would one day be replaced by Darwin's tree, it marked the first serious attempt to organize life according to natural principles. Life is a system, and every part of it matters. Aristotle dissected birds, fish, insects. He opened animals not out of cruelty, but out of wonder. He was the first to describe the beating chambers of a heart, the veins that carried blood, the organs that digested food. His methods were empirical. He saw, he touched, and in many ways, he was right. He observed that chick embryos form organs in stages, what we now call embryology. W. He noticed how different animals have different kinds of reproduction. W. He understood that function followed form. W. He understood that function followed form. But he had vision, and when he asked, what is the soul, he didn't mean spirit. He meant the life force. What animates a plant? What drives an insect? What gives a human being its spark? He tried to answer it biologically. In fact, his book on the soul is less mysticism than it is early neuroscience. Long before Linnaeus, Aristotle grouped animals based on shared characteristics. Those with blood versus those without. Those with lungs versus those with gills. Those that lay eggs versus those that bear live young. He didn't get everything right, of course. He believed bees collected honey from flowers, correct. But he also thought flies were born from mud, not so much. Still, what matters is this: he believed the natural world could be understood. That classification wasn't arbitrary. It reflected underlying truth. Today, our DNA trees are more accurate, but they still echo his categories. We still ask, what do organisms share? What makes them unique? That's Aristotle's question. Now you may ask, what does any of this have to do with space? Because if we are to search for life beyond Earth, we must first define what life is. What makes something alive? Does it breathe? Does it breathe? Does reproduce? Does respond to stimuli? These were Aristotle's questions. When we examine Martian soil or scan exoplanet atmospheres, we use biological signatures: carbon, oxygen, methane, because we believe, like Aristotle, that life leaves patterns. We look for water because we know that on Earth, life depends on it. That idea that biology is tied to conditions begins with Aristotle. He saw that animals adapt to their environment, that desert creatures differ from sea creatures. He understood context, and context is what drives the search for extraterrestrial life. In dissecting animals, Aristotle noticed similarities. He saw that birds, reptiles, and mammals had common organs, but with variations. He didn't have the concept of evolution, but he saw patterns of design. Today, evolutionary biology builds on this. The idea of homology, shared ancestry reflected in similar structures, finds its roots in Aristotle's method of comparison. He was trying to understand why animals were built the way they were, and though he lacked Darwin's mechanism, he had the eye of a comparative anatomist. He saw unity beneath diversity, and that vision powers biology to this day. When Aristotle spoke of the soul, he didn't mean a ghostly essence. He meant the principle of life. Plants had a vegetative soul. They could grow, reproduce. Animals had a sensitive soul. They could move, sense, feel. Humans had a rational soul. They could think, reflect, imagine. This was a hierarchy of function, not of holiness, and it laid the groundwork for what we now call psychology. How do perceptions arise? How do emotions manifest? What makes consciousness? Modern neuroscience traces circuits in the brain, but it still asks Aristotle's question: what is the relationship between mind and body? Where does intention arise? How does biology create thought? Not all of Aristotle's observations were correct. He thought men had more teeth than women. He believed the brain cooled the blood. He believed some fish had no lungs, true, and others laid eggs from their mouths, false. But this is the core of science: observation, hypothesis, correction. He wasn't infallible, but he was systematic. He started with nature, not mythology, and by doing so, he moved biology from speculation to study. Today, peer-reviewed journals, double-blind studies, and data-driven trials may look different, but the spirit is the same: observe, record, test, change what you thought if the evidence demands it. Aristotle looked at the stars and saw perfection. He looked at life and saw striving. And now, 2,300 years later, those visions converge. Space biology is real. We study how microgravity affects muscles, how radiation impacts DNA, how organisms mutate in orbit. On the ISS, we grow plants, we monitor bacteria, we examine how reproduction, digestion, and cell repair function beyond Earth. And when Elon Musk dreams of Martian colonies, or NASA imagines seed vaults on the moon, they're invoking not just engineering, but Aristotle's biology. Because if life expands to space, it must adapt. And to understand that adaptation, we must know what life is. That's the question Aristotle never stopped asking. Aristotle's biology is more than outdated diagrams. It's a philosophy of study. Start with what you can see, break it down, compare it, classify it. Whether peering through a telescope or a microscope, the goal is the same: find the order in the chaos, understand the hidden architecture of life, and never assume that what is seen is all that there is. We've walked with Aristotle from the stars to the sea. We've watched him dissect, describe, and define. But more than his answers, it's his questions that endure. What is life? What does it want? What patterns does it follow? In a world where we edit genes, build AI, and launch probes to Europa, the ancient biologist still walks beside us. Because in every heartbeat we measure, every cell we map, every signal we scan for on alien worlds, we are tracing the same line of inquiry. What lives? Why does it live? And could it live elsewhere? And in many ways, it still is ours. We've descended into the mysteries of life with Aristotle. We've watched him probe the secrets of fish, birds, and beasts, not out of idle wonder, but to map the logic of living systems. But now, let us turn to a different tool in his intellectual workshop: logic. Not just what we see, or touch, or dissect. Because Aristotle didn't just teach us what to observe. He taught us how to reason, and that changed everything, from medieval scholars to modern science labs, from courtroom arguments to NASA control rooms. So, buckle up, because what begins with syllogisms ends in rocket fuel. Before Aristotle, people reasoned intuitively. They persuaded. They even philosophized. But there was no system, no formal rules for when an argument was sound or when it just sounded good. Aristotle changed that. He invented formal logic, the science of valid inference. If all men are mortal, and Socrates is a man, then Socrates is mortal. That simple structure, premise, conclusion, is called a syllogism. And with it, Aristotle gave the world its first engine of thought. Let's pause a moment. Imagine you're programming a computer. You write IF. All oxygen requires hydrogen, and this sample lacks hydrogen, then this sample lacks oxygen. You're not writing Greek philosophy, you're writing logic. That is Aristotle. His rules of thought became the blueprint for everything from computer science to forensic reasoning. Without formal logic, there is no algorithm, no code, no AI. So when GPT-4 answers your questions or NASA software calculates a trajectory, it's doing what Aristotle taught, breaking truth into steps. One of Aristotle's most famous contributions is called the square of opposition. It's a way to test truth by comparing related statements. Law. All humans are mortal. Some humans are not mortal. No humans are immortal. Some humans are mortal. He mapped out how these ideas relate. What contradicts what implies what. It sounds abstract, but it's everywhere. Detective work, medical diagnosis, scientific modeling. Suppose a spaceship loses contact. What happened? Could be a power loss. Could be a signal block. Could be destruction. Each hypothesis generates new questions, and that structure, how we test truth against alternatives, goes back to Aristotle's logic. Here's where it gets cosmic. Think about planetary motion, Kepler's laws, Newton's gravity. To test those models, you need more than data. When astronomers look at a galaxy spinning too fast to hold itself together, they ask, is our gravity model wrong? Or is there unseen matter? They form a hypothesis. They make predictions. They compare. And each of those steps follows Aristotelian logic. You identify premises. G. Draw conclusions. Modern science didn't begin with a microscope. It began with logic. Aristotle's most famous rule, a thing cannot be and not be at the same time in the same respect. This sounds obvious, but it is the foundation of rational thought. You cannot say, the rocket launched and did not launch. It's this law that separates dreams from data, myth from model. Even in quantum mechanics, where particles seem to be in two places at once, we carefully define how and why. Because contradictions, real contradictions, break the system. Without consistency, no science stands. And Aristotle taught us that. How do space missions work? Hypothesize an orbit. Calculate the fuel. I build a simulation. I brood logic checks. Launch. I run logic checks. Every step depends on reasoning. When engineers build autonomous navigation for Mars rovers, they use logical rules. It's conditional logic. Aristotle's if-then thinking. He didn't know what a rover was, but he built the mental hardware it runs on. Aristotle didn't keep his ideas locked in scrolls. He taught them at the Lyceum, his school in Athens. His students copied them, preserved them, spread them. Through Islamic scholars in Baghdad, through medieval universities in Europe. And in time, those seeds grew into the Enlightenment, into calculus, into computing. The rules of logic became the rules of civilization. And to this day, when a student learns to prove a theorem, or a lawyer argues a case, or a coder writes a program, they are heirs of Aristotle. Many credit Galileo or Bacon with the scientific method, but Aristotle laid its bones. Observe the world, ask questions, form hypotheses, form hypotheses, use logic to test them. He believed we could move from what is known to what is unknown. That knowledge isn't static, that truth can be built, and he gave us the toolkit to do it. Fast forward. Today's AI, like the one you're hearing right now, isn't magic. It's rules, structures, models. Neural networks run calculations, but at their core is logic. Input, Sikabai, processing. Sikabai, output. If this, then that. When DeepMind trains an agent to solve a maze, it's using Aristotelian chains of deduction. When an AI doctor reviews symptoms and suggests a diagnosis, it's using formal inference. Aristotle didn't build computers, but he imagined the software of thought. Some say logic is cold. But Aristotle didn't see it that way. To him, logic was a path to clarity, to justice, to understanding. He knew that reason, used well, could prevent wars, could solve disputes, could advance knowledge. Logic isn't the enemy of emotion, it's what keeps emotion honest. And when you listen to debates on ethics, on policy, on the future of humanity, you'll hear Aristotle echoing still. Of course, Aristotle got things wrong. He believed heavier objects fall faster. He thought women had fewer teeth. He classified comets as atmospheric. But in logic, he built something nearly indestructible. His laws, identity, contradiction, the excluded middle still govern rational thought. Even in quantum physics, where uncertainty reigns, we use logic to frame uncertainty. We ask, what can we say? What must we admit we don't know? That humility of logic meeting mystery was something Aristotle understood. Today, in NASA mission control, every screen shows data, but more importantly, it shows logic trees. If signal lost, check antenna. If temperature rises, trigger fail. Safe. These aren't random decisions, they're syllogisms in action. And in classrooms around the world, students learn critical thinking. They ask, is this argument valid? Is this conclusion supported? That's logic. That's Aristotle. Aristotle believed the universe was understandable, that if we think clearly enough, we can find its order. He was wrong about the stars, wrong about motion, but he was right about thinking. He gave us a method that lets us be wrong and still move forward, that lets us build rockets, diagnose illness, program intelligence. He gave us reason, and with it, we reached the stars. Aristotle believed the universe was understandable, that if we think clearly enough, we can find its order. He was wrong about the stars, wrong about motion, wrong about ether, but he was right about thinking. He gave us a method that lets us be wrong and still move forward, that lets us build rockets, diagnose illness, program intelligence. He gave us reason, and with it, we reached the stars. Imagine standing before a crowd 2,300 years ago. You are the great Aristotle. You've categorized animals, you've invented logic, you're the teacher of kings. When you speak, people listen, and when you say, the Earth is at the center of the universe, well, who would dare argue? This is how power works in knowledge. Authority becomes gravity, and Aristotle's words became intellectual law. His geocentric model, Earth at the center, heavens orbiting in crystalline spheres, was elegant, logical, certain. But it was wrong, and for 2,000 years, that elegant era would shape the skies. Aristotle believed everything had a natural place. Heavy things sank, fire rose. The Earth sat motionless in the middle of the cosmos. Above it, perfect spheres turned in eternal circles. The stars were fixed. The planets wandered in loops. This wasn't mythology, it was observation plus reasoning. But there were cracks. Why did planets sometimes move backward? Why did some stars change brightness? These questions would haunt astronomers for centuries. But few dared to challenge the master, because Aristotle's model wasn't just science, it was philosophy. And to doubt it was to doubt reason itself. One of Aristotle's most persistent errors wasn't about stars, it was about space. He believed nature abhorred a vacuum, that empty space could not exist. Why? Because in a void, motion becomes meaningless. There's no resistance, no direction, no cause. So, he declared, there are no vacuums. This idea, horror vacuum, would dominate physics for 2 millennia. Even when early scientists tried vacuum experiments, they were dismissed. Impossible, they were told. Aristotle says no. His experiment showed Aristotle was wrong, yet that wrong belief had lasted 2,000 years. That's the power of a beautiful idea. It can survive longer than it should. Aristotle believed that heavier objects fall faster than lighter ones. Why? Because they have more earth, more desire to reach their natural place. And to Aristotle, this was self-evident. Drop a rock and a feather, and the rock lands first. What he didn't account for was air resistance. But without tools to test, he had no reason to doubt. So his view held for nearly 2,000 years. It wasn't until Galileo rolled balls down inclined planes in the 1600s that the truth emerged. Mass doesn't affect fall speed in a vacuum. On the moon, where there's no air, a hammer and feather fall together. NASA proved it in 1971. And in that single moment on lunar soil, Aristotle's greatest mistake became a lesson in humility. It's easy to blame Aristotle for these errors, but the real culprit wasn't the man. It was the system that treated his ideas as infallible. Scholars repeated his claims. Books canonized his thoughts. The church merged his cosmos with theology. So when Copernicus proposed a sun-centered system, it wasn't just astronomy at stake. It was Aristotle's reputation. When Galileo used a telescope to spot moons orbiting Jupiter, he wasn't just seeing science. He was committing heresy. And when Newton wrote Principia, replacing Aristotle's natural motion with universal gravity, he didn't just revise physics, he overthrew a 2,000-year-old kingdom. Each error had ripples. Aristotle's belief in circular motion delayed elliptical orbit theory. His insistence on a finite, closed cosmos blocked the idea of an infinite universe. His rejection of the vacuum delayed fluid dynamics, pressure science, and even aeronautics. In other words, Aristotle's mistakes held back Newtonian physics, space travel, rocket propulsion. When NASA launches a rocket today, it does so in defiance of Aristotle's laws of motion. Yet here's the paradox. Without Aristotle's system, those later geniuses might never have had a framework to rebel against. He gave questions, and even his wrong ones were the right ones to ask. This is the heart of it. In science, error isn't failure, it's fuel. Aristotle's geocentric model was wrong, but it created models, maps, and mathematics. His physics was flawed, but it asked what causes motion. His vacuum denial delayed technology, but it forced thinkers to test nature more carefully. Each correction became a breakthrough. It's like navigating a maze. Every dead end sharpens your sense of direction, and in this way, Aristotle's wrong turns paved the road to space exploration. By the 1600s, thinkers began to break from Aristotle. Copernicus moved the sun to the center. Kepler replaced circles with ellipses. Galileo showed the moon wasn't perfect. Descartes replaced soul-driven motion with mechanical laws. Each rebel was shaped by Aristotle's shadow. They learned his rules, then broke them. And by the time Newton arrived, the cosmos had changed forever. Gravity replaced natural place. Force replaced essence. Void became part of reality. The telescope replaced the eye. The experiment replaced assumption. And with each step, Aristotle's influence evolved. You might think these errors destroy his reputation. They don't. Because Aristotle never said, "Believe me no matter what." He said, "Start with observation, use logic, seek causes." He laid the method even if his conclusions were flawed. That's why scientists still quote him. That's why philosophers still debate him. That's why AI systems, logical engines, and scientific papers echo his structure. He wasn't the final word. He was the first sentence. And in that, he was never wrong. Perhaps the most profound lesson Aristotle offers isn't in his brilliance. It's in his errors. Because every scientist, every engineer, every explorer must face this question: what if I'm wrong? It's not shameful, it's essential. And Aristotle gave us the tools to correct Aristotle. That's the greatest gift any thinker can leave. So as we journey toward stars, toward Mars, toward the edges of known space, we do so with Aristotle behind us, not as an idol to follow, and that the boldest path forward is paved with the courage to let go of even the most beautiful ideas. That is how science grows. That is how humanity ascends. And that is how Aristotle, in being wrong, helped us become right. We've seen Aristotle rise through brilliance, inquiry, and innovation, and we've seen him stumble, trapped by the limitations of his time. But the story doesn't end there, because Aristotle's words didn't vanish into dusty scrolls or vanish with the fall of Athens. No, they traveled across deserts, through libraries, into the hands of astronomers and scholars who lit candles in the dark corners of history. This is the part of the story few tell, the unexpected afterlife of Aristotle in the Islamic Golden Age, a time when science flourished in the very lands where the night sky was once mapped by nomads. This is the rebirth of Aristotle under new stars. When the Western Roman Empire collapsed, so too did much of the infrastructure that had once preserved classical knowledge. Libraries burned, schools closed, scrolls were lost. Europe entered the Dark Ages, a time of turmoil and intellectual stagnation. But knowledge, like life, finds a way. Far from the ruins of Rome, a different world was rising. In Damascus, in Baghdad, in Cairo, Islam had unified a vast region stretching from Spain to the Indus. And with that unity came a thirst, not just for conquest, but for wisdom. The Quran itself spoke of knowledge as a virtue. And so, the scholars of this new civilization began collecting texts from Persia, from India, from Greece. And among the treasures they sought most, Aristotle. In the 9th century, in Baghdad, the Abbasid caliphs established the Beit al-Hikmah, the House of Wisdom. It wasn't just a library. It was a research institution, a translation center, a hub of cross-cultural fusion. Greek texts were translated into Arabic. Sanskrit mathematics was studied alongside Persian astronomy, and leading these efforts were polymaths, men of vast intellect and curiosity who treated Aristotle not as ancient dogma, but as a springboard for discovery. Hunayn ibn Ishaq al-Kindi, al-Farabi, Averroes, Ibn Rushd. These were the minds who brought Aristotle back to life. Al-Farabi, a philosopher and scientist of the 10th century, was so influenced by Aristotle that he became known as the second teacher, second only to Aristotle himself. He saw Aristotle's work as a system of logic and metaphysics that could align with Islamic theology. He studied the categories on interpretation and the metaphysics, refining Aristotle's logic and applying it to the governance of society, ethics, and the natural world. He wrote of the ideal city, much like Plato before him, but always with Aristotle as his compass. Through Al-Farabi, Aristotle wasn't just translated, he was transformed. A century later, in Islamic Spain, Averroes, or Ibn Rushdi, took up Aristotle's mantle. He wrote exhaustive commentaries on nearly every one of Aristotle's works, line by line. Where earlier scholars preserved, Averroes interpreted. He saw in Aristotle a framework that could support a rational understanding of faith and nature. He debated whether the soul was immortal. He argued over Aristotle's view of the cosmos. He tried to reconcile religion with philosophy, not by rejecting Aristotle, but by debating him. His writings would later be translated into Latin, igniting the scholastic movement in medieval Europe. Without Averroes, Aristotle might never have returned to the West. While philosophers wrestled with Aristotle's logic, scientists took his methodology further. Enter Ibn al-Haytham, known in the West as Alhazen. He read Aristotle, but didn't worship him. Aristotle believed vision came from rays emitted by the eyes. Alhazen tested that idea and disproved it. Through experimentation, dark chambers, pinholes, lenses, he showed that vision comes from light entering the eye, not from the eye itself. This was revolutionary. Alhazen didn't just refute Aristotle. He used Aristotle's own method, observation, reasoning, experimentation, to go beyond him. It was science, evolving. In the realm of the stars, Aristotle's geocentric model was dominant. But Islamic astronomers weren't content with its flaws. Al-Battani improved on Ptolemy's tables, refined planetary positions, and introduced sine functions to trigonometry tools still used in space science today. He observed that the Earth's axis tilted and the distance to the Sun changed, data that would later support the heliocentric model. Nasir al-Din al-Tusi developed models of planetary motion that Copernicus would later adapt. These were not rebels. They were refiners, challenging Aristotle not out of rejection, but out of respect. They didn't destroy his cosmos, they remodeled it. What made this era extraordinary wasn't just the scholarship, it was the fusion. Indian mathematics, Persian medicine, Islamic theology, all coming together under the light of Aristotle's logic. It was the first great globalization of science. Manuscripts were copied, debated, passed from Cairo to Cordoba to Constantinople. Ideas didn't belong to empires, they belonged to the human spirit. And at the center of it all was the philosopher from Stagira. By the 12th century, these Arabic translations and commentaries began to reach Europe via Sicily, Spain, and the Crusades. European scholars, starved for knowledge, devoured them. In places like Toledo, teams of Christian, Jewish, and Muslim translators worked side by side. They didn't just translate Aristotle, they translated Aristotle as interpreted by Islamic thinkers. This wasn't a return to the Greek original, it was a rebirth, layered with centuries of insight, and it would trigger a transformation. In Paris and Oxford, thinkers like Thomas Aquinas read Aristotle and Averroes. They debated logic, the soul, causality. Aquinas tried to merge Aristotle with Christianity, arguing that reason and faith could coexist. This synthesis created scholasticism, the dominant philosophy of medieval Europe. And through it, Aristotle became a central figure again, no longer pagan, but baptized into the academic canon. From Baghdad to Bologna, the flame of reason burned on. When we talk about global collaboration in science, about multicultural teams at CERN or NASA, we often forget it's not new. Aristotle's legacy survived because of collaboration, because Muslim scholars translated Greek into Arabic, because Jewish scholars translated Arabic into Latin, because Christian monks preserved and debated it, because knowledge isn't owned, it's shared, and the same logic that Aristotle taught, the same observational rigor, the same passion for truth, it pulsed in the hearts of those scholars, and it pulses still. Today, we study exoplanets and quantum entanglement. We launch telescopes and build AIs, but the spirit of inquiry, of asking better questions, remains Aristotelian. When NASA engineers debate a mission's logic tree, when physicists at CERN test symmetry violations, when AI systems weigh decision branches, they are still using the tools forged in Baghdad and Athens. That's the legacy of the Islamic Golden Age, not a museum. A bridge between worlds, between past and future, between error and truth. And across that bridge walked Aristotle. So the next time you look up at the stars and wonder how we came to understand them, remember it wasn't just Newton or Galileo. It was Alhazen with his camera obscura, Al-Farabi with his logic, and above them, a teacher from ancient Greece whose ideas traveled farther than he ever could have imagined. Through scrolls, sand, and centuries, Aristotle lived again. And because of that, so did the dream of knowing the universe. From the Aegean shores to the deserts of Baghdad, from cathedral libraries to NASA control rooms, we've followed Aristotle's long shadow across time and continents. But now, we arrive at the final horizon. Because the story of Aristotle isn't confined to the past, it echoes into the cosmos. And this final chapter isn't just about history. It's about futures. It's about the modern world of quantum fields and distant galaxies, and how, somehow, the voice of a man who lived 2,300 years ago still whispers through the equations. This is Aristotle's legacy in modern space science. Aristotle believed in a perfect, unchanging universe. The heavens were spheres of crystal. The stars were eternal. The earth stood still. But modern astronomy reveals a far stranger picture. Galaxies swirl in spirals and smash together. The stars are born and die in supernovae. Black holes bend space-time. The cosmos isn't calm. It's violent, evolving, and expanding. And yet, Aristotle's method remains. Because to understand this new universe, we still ask the questions he asked. What is the cause of motion? What are the basic elements? What is the nature of change? Only now, our spheres are electromagnetic fields. Our elements are quarks and leptons. But the logic, the hunger to classify, to predict, to explain, is Aristotelian at its core. One of Aristotle's deepest commitments was the idea that everything has a purpose, a final cause. To him, fire rises because it seeks its natural place. The moon moves in circles because that's its nature. Modern physics rejects teleology, that idea of built-in purpose, but it replaces it with a different kind of structure, laws. And those laws, relativity, quantum mechanics, thermodynamics, are still built from categories, distinctions, and definitions. In that sense, every physics equation is a descendant of Aristotle's syllogisms. If all particles have spin, and electrons are particles, then electrons have spin. Logical reasoning, ordered causality, classification. These are the building blocks of physics. Even when we study chaos, we do so with the framework he helped design. But NASA, ESA, SpaceX, all modern space agencies use something Aristotle helped invent. When engineers test a spacecraft system, they use conditional reasoning. If the thruster fires and the trajectory doesn't adjust, then the issue is not with fuel supply. This kind of troubleshooting traces its ancestry to Aristotle's logic trees. Even the software that runs spacecraft navigation is built from logic gates. Yes-no sequences that mirror Aristotle's truth tables. So, though the sky he imagined no longer holds, the methods he created now orbit it. Aristotle asked, is the universe finite or infinite? Does it have a beginning, a shape? Today, we ask the same armed with data from the James Webb Space Telescope, the Large Hadron Collider, and the cosmic microwave background. What we've discovered would shock Aristotle. Awe. The universe had a beginning, the Big Bang. It's expanding, not static. It might be flat, infinite, or curved in dimensions we cannot yet grasp. But in asking how we know these things, we still follow his lead. Observe. Compare. Deduce. Explain. Even as we dismantle his conclusions, we honor his process. Remember Aristotle, the biologist? The man who dissected cuttlefish and studied chick embryos. Today, his drive to classify and understand life continues. On Mars, on Europa, in the Atacama Desert, in simulations of early Earth conditions. Astrobiologists ask, what defines life? How does it arise? Force. How does it arise? Force. Could it emerge from different chemistries? Aristotle asked, what is the soul? What is consciousness? What is consciousness? He defined life by its capacities, nutrition, reproduction, sensation, rationality. We use biosignatures and behavior patterns. In both cases, we seek the invisible through the visible. And that is an Aristotelian instinct. It may seem like a leap from scrolls to silicon, but Aristotle also stands at the root of artificial intelligence. Why? Because AI is built from logic. And formal logic, syllogisms, conditionals, structured reasoning begins with Aristotle. Modern AI systems perform tasks like Lyceum natural language processing, decision trees, deductive problem solving, all of which echo the structure of Aristotelian argument. Even advanced models like neural networks are trained on classification, the same impulse that led Aristotle to divide animals by blood, limbs, and reproduction. He built the first decision trees. We turn them into algorithms. Perhaps most remarkably, Aristotle believed that knowledge had a telos, a purpose, that humans were not just curious, they were meant to understand. And modern cosmology sometimes asks the same thing. Why can the universe be understood? Why do physical constants allow life? Are we observers or participants? The anthropic principle, which posits that the universe appears fine-tuned for life, echoes Aristotle's belief that form follows function. Even in an age of probabilistic physics and chaotic systems, we're haunted by the same philosophical ghosts. Why this universe? Why these laws? Aristotle's worldview was deterministic, ordered, logical. Quantum mechanics is not. Particles exist in superposition. Probabilities replace certainties. Observation changes reality. It seems to violate Aristotle's law of non-contradiction. A thing cannot both be and not be. Yet even in this, Aristotle's influence lingers, because we measure uncertainty in structured ways. We define probability distributions. We build mathematical models. We may not know where an electron is, but we know how to describe what we don't know. And that, paradoxically, is a very Aristotelian achievement. In the end, what did Aristotle want? He believed that nature made sense, that reason could unlock its secrets, that conviction survives every revolution, every paradigm shift, every overturned theory, and it drives the questions we ask now. Sukkah, can we terraform Mars? Sukkah, will we find intelligent life? What lies beyond the observable universe? These aren't just technical questions, they're philosophical. And in asking them, we step into Aristotle's shoes. We become philosophers of the cosmos. In every lab, every observatory, every classroom and control room, the fire Aristotle lit still burns, not because he was always right, but because he dared to ask. He sought causes when others told stories. He measured when others mythologized. He built systems, not to trap nature, but to trace it. And in doing so, he gave us a blueprint for curiosity. That is why he matters. Not because the stars are spheres, but because the mind is ordered, questioning, reflective. So now, as we gaze across the vastness of space, launching missions to the edge of the solar system, building telescopes that peer into the birth of time itself, what remains of Aristotle? Everything. The method, the structure, the hunger to explain. He was the first to say, let's observe. And though his cosmos is gone, his curiosity endures. In us, in every scientist, in every question, in every glimpse of the stars. Because ultimately the quest he began was not for Athens, not for Greece, but for truth. And truth knows no end. Thank you for joining us on this journey through time, thought, and the cosmos. If you found this exploration as fascinating as we did, consider subscribing to Eridanus Light. Here, we bridge the ancient and the cosmic, the philosophical and the astronomical. Like, comment, share your thoughts. And as always, keep your eyes on the stars and your mind in the question. This is Eridanus Light.